What's up, everybody? In this next video lesson, we're going to talk about half-lives and how to calculate half-lives. First, let's start with this concept that some substances go through multi-stage decay. What happens is, remember, anything bigger than bismuth has no stable isotopes, and anything that is bigger than bismuth, regardless of the number of protons or the number of neutrons, is a radioisotope. So it's going to go through decay. For example, uranium, which is really big, the largest naturally occurring element on Earth, in fact, goes through alpha decay to come thorium, then beta decay, alpha, 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 beta, 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 alpha. You get the idea. Every time it goes through decay, it gets slightly smaller, but this is bigger than bismuth, and so it is also a radioisotope. And eventually it gets down to a point where it's an isotope that is stable because it's smaller than bismuth. Lead-206 is a stable isotope. Over here, we have a list of the half-lives that each one of these decays would occur. Half-life, which we'll define on the next page, is the amount of time for half the original sample to be decayed into the new substance. And so sometimes it's measured in years, sometimes it's measured in days, sometimes it's measured in seconds, but it's an amount of time that is needed to reduce the concentration by half. So each stage has its own half-life. And you can imagine a sample of uranium-238. Some of these are decaying at different rates, and so this is a rather complicated system. It's not all thorium, because thorium is going to decay in 24.5 days, but then the protactinium is going to decay in 1.414 minutes. And then we'll go back up to uranium, but at a different mass, and then it's going to go down again to thorium. So we've got many different isotopes in this system, and they all have different half-lives. So each stage has its own half-life. So I've mentioned the concept of half-life a number of times on that last slide, so let's define it. It's the time required for half of the nuclei of a sample of a radioisotope to decay into a more stable product. It can be less than 1 second, and it can be up to billions of years. This little table down here shows a couple of different radioisotopes. Some are small radioisotopes, like hydrogen with 2 neutrons in the nucleus is called tritium. Its half-life is 12.26 years. So after 12.26 years, let's say I have 10 grams of this stuff. After 12.26 years, I should have 5 grams. And then after another 12.26 years, I don't reduce it to 0. And that's a common misconception, that it goes down by 5 and then it goes down by 5 again. But actually 5 turns into 2.5. Remember, it's half of the next sample. So 10 turns to 5, turns to 2.5, turns to 1.25. And it gets even lower, and it gets even lower, and it gets even lower. And eventually we get down to 1 particle, 1 nucleus. And that nucleus has an undefined half-life, because we can't have a half-life for just 1 particle. That nucleus might decay instantly, or it might decay many, many, many hundreds of years later. We don't know. We can only calculate the half-life if there's more than one of the particle. So we've got other substances like carbon-14, which has a half-life in 5,730 years, and other things like this one over here, polonium, which is in fractions of a second. So you've got days, you've got years, you've got hours, you've got seconds. So everything has a different half-life, and that half-life is measurable and it's consistent. This potassium will decay in 1.25 times 10 to the 9th years. That's a really long time, but it is a known value that we can calculate and measure. So what does it look like when we graph the half-lives of a substance? What we have here is bismuth-210 and has a half-life of 5 days and undergoes alpha decay to become thallium-206. So let's say we start with 100 grams of that substance, bismuth. After 5 days, you've got 50. After 5 more days, it's 25. 5 more days, 5 more days, 5 more days. We say the half-life is 5 days. It's an amount of time, not an amount of substance. We can take a look at this graph, and we can see that eventually it'll approach 0, but it'll never touch 0, because once we get down to 1 particle, as I mentioned on the last slide, we can't express a half-life any longer for 1 particle. But it approaches 0. What type of graph is this? This is known as an exponential decay graph. And all half-life graphs look the same, no matter what it is. Some just have longer time periods along the horizontal. Some have shorter times on the horizontal axis, but they all look the same. They start out at their highest at time 0, and depending on the half-life, it will decay in a exponential decay sort of way. Now, because we're talking about exponential decay type situations, the math isn't linear algebra by any means. It's exponential, it's logarithmic. And so calculating half-lives gets a little bit tricky. We have made for you this formula that you can follow as long as you know what each one of the 4 variables means. You take an original amount of sample, we call that A at time 0. The little 0 down here in the lower right-hand corner means it's original. It's the time 0, original amount. You multiply that by 1/2, and that 1/2 is multiplied by the T over big T power. So you need to know the time elapsed, that is the same unit that the half-life is, divided by the half-life of the substance. The known value for big T is the half-life. And you multiply those together and you can solve for A, the amount of substance. So let's put this into practice. We've got an example here. We've got iodine 131 has a half-life of 8 days. So that's my big T. And how many grams will be remaining of an 80-gram original sample after 3 weeks? Now, weeks are not in days. We need to convert weeks to days. So 3 weeks is 21 days. So I've got an original amount, 80 grams. I've got a time elapsed, which is 21 days, divided by the half-life, which is 8 days. And I punch this into my calculator, and I get a final amount of 13.0 grams. Now, it's important that you can do this in your calculator, and I recommend doing steps in this order. I'd take the exponent and figure what that is first, 21 divided by 8. Then I would take 0.5 and take that to the exponent power, and I'll get a number. And then I'll take that number and multiply by 80.0 grams. And so if you screw up the order of operations, this might not work out for you. And so take it step by step in your calculator. Use this formula if you're trying to calculate an amount if you know the half-lives, but this gets a little bit more complicated if you know the amounts and you're trying to calculate the half-lives. So we have rearranged this formula to a new formula that we'll give to you so you can just plug in the numbers and solve for the missing variable. But if you're familiar with logs, you should be able to do something like this and rearrange for T or big T if you want to. But if you don't want to, check out this next equation. What you're looking at is that last equation, but this time it's rearranged and solved for T, where T is the half-life. So with this formula rearranged, we can tackle something like this, where I have a starting amount and a final amount, and I have a time elapsed, and I'm trying to figure out what the half-life is. So I can put 600 seconds in for T. I can put A at time 0, which was 500 grams, and then A at the end time, which is 16.63. And once I've got that, I plug it in my calculator, and I can solve for T, which is the half-life. And when I punch this into my calculator, I get a final number of 122.2 seconds, and that will be my half-life. Once again, you need to be careful when you plug this into your calculator so you don't screw up the order of operations. What I did is I took the numerator and I figured that out. I took 600 times the natural log of 2, and I stored that number in my calculator. And then I did the denominator. I did the natural log of 500 over 16.63, and then I took those two numbers saved in my calculator's memory and I divided them. I took the numerator divided by the denominator, and I got 122.2 seconds. So with those two formulas, you could tackle some questions like you see the ones in the notes here. And we're going to do these in class, so you don't need to worry about them now. But it's not going to be just as simple as plug and chug. We're going to try and add a couple of wrinkles into it. So these are good practice that we're going to do in class. And if you want more practice, there's a worksheet in the student files. Well, that takes care of this video lesson on half-lives and how to calculate them. Thanks for watching.